Alright, so this video here is just going to give us some quick rundown on some of the rules for derivatives here. So, the power rule, just real quickly, if you take the derivative of something of x to the n power, this is just n times x to the n minus 1. Now there's another bunch of rules here that we have for functions here. And so before we get into some of the special rules like the product rule, the chain rule, and the quotient rule, let's look at the derivatives of other functions as well, because those are where we're going to see the benefit from these. So we have two other functions that we are going to want to look at here. And we have e to the x, which the derivative of e to the x is actually, whoops, got ahead of myself here. Derivative of e to the x is simply equal to e to the x. So that's a very easy one to remember. And then we also have the natural log. So the derivative of the natural log is simply 1 over x. Now I'm going to make one other kind of additional rule here. Even though this really comes as a result from one of our special rules, it's one that we encounter so often that it's kind of nice just to remember it offhand. The derivative of derivative of e to the kx is equal to k times e to the kx. So, for example, what we're saying with that one is if we have the derivative of e to the negative 5x, for instance, well, the k in this case is the number, and the negative is part of that number, and so this would be equal to negative 5e to the negative 5x. And now we're going to need to know these special rules, these basic rules here, in order to do derivatives here. Now, one of the rules here that I'm not even going to write down, they're called like kind of basically linear properties where, hey, if you multiply by a constant, you kind of just ignore the constant and then just do the derivative of the other thing. And the easiest way to explain that is just to look at a simple derivative here of like x cubed minus 4x squared plus 5x plus 6. And so even though this is not just a single x to the n, we just look at each individual term here. So if I look at this first x cubed, that of course gets me a 3 that comes down in front, subtract 1 from the exponent, and you get 3x squared. And then I'm going to do the arithmetic in my head here. I've got a minus 4. I'm going to be bringing down a 2 or multiplying by a 2 out in front, and so that would be minus 8. And then it would be x to the first power, but when we have something to the first power, we don't write the exponent. And then the 5x, there's a couple ways to think of it. Sometimes some books will have it where you have the derivative of simply just k to the x, k times x is just equal to k. But you can also look at it this way here. If I go to derivative of 5x, and I think, okay, well, it's to the first power here. And I keep writing equals with my derivatives here, which is not what I'm wanting to do. So if I think of this as 5x to the first power, that would just be 5 times 1, which is 5, x to the 0 power, but then anything to the 0 power is just 1, and so I get 5. So either way you can remember it. I just remember that whenever you just have 5x, you just get that number that comes down in front, so you get 5. And then a derivative of a constant is always 0, so the derivative of 6 is just 0. So that would be my derivative of this function here. So with that being said, let's look into some of the actual rules here. So the first rule we're going to look into is the product rule here. And so the product rule is where we have the derivative with respect to x, and we have two functions that we're multiplying together. So f at x times g at x. And so if we take the derivative of two functions, there's a special rule that we have to follow. And it's basically, it's the derivative of the first term times the second plus the first term times the derivative of the second. Okay, so let's just look at a couple examples of that. An easy example here, let's just start with two polynomials here. So let's look at the derivative with respect to x of 3x squared plus 5x plus 1 times 2x cubed minus 3x. So in this case, this first term here is your f at x, and then the second term here is your g at x. And now you want to always make sure to keep parentheses with these things. And you want to keep parentheses so that you don't get marked off, because if you don't include your parentheses, technically your answer is not correct. So let's just follow the rule here. So it's the derivative of the first. So this is equal to derivative of the first. Well, that would be 6x plus 5. But that's a quantity, so I'm going to put parentheses around that. And then it's times the second. And then it's going to be plus the first term times the derivative of the second. So the derivative then would be, well, I'd get 6x squared minus 3. Now, depending on what your course is requiring, you might need to multiply all these out and simplify things together. I always say that is kind of a matter of what a professor expects as simplification. Now, if I look here, though, I'm not going to do it. You could have just, in this first step, multiplied everything out, taken a derivative. And, you know, or you could just do what we did here. That's a way you can verify it. I'm not going to verify it. But let's look at a couple other examples of the product rule, because the product rule really comes into play when you have something like this, where you have the derivative with respect to x of e to the 4x times, like for instance, let's say just x squared plus 3x minus 5. Okay, so in this case, we still have an f at x and g at x. My f at x here, this is my f at x, and this here is my g at x. And there is absolutely no way to do the derivative of this without using the product rule, because you can't multiply this out. Well, I mean, technically you could multiply it out, but it would be stupid to do that, because you'd just have to use the product rule 3 times then to take the derivative. There's no way to multiply it out and get a nice polynomial. So let's just go through the rules here. Well, derivative of e to the 4x, just going back up here, well, that's k times e to the kx. So this would be derivative of the first. So derivative of the first is then 4 e to the 4x. And I'll go ahead and write parentheses, because we always said it's a good idea to keep parentheses here. X squared plus 3x minus 5. And then plus e to the 4x, which is the first term, times the derivative of the second. The derivative of the second term would be 2x plus 3. Now, in this case, you can simplify these out more here, because what do we have here? notice that we have an e to the 4x in both of these two terms, because we really have two terms. Why do we have two terms? A term is separated by like a plus or minus, is the way I like to think of it. I mean, that's not technically true, but this is one whole term that we haven't multiplied out, but it's one whole term there. And so I could rewrite this as e to the 4x times 4 parenthesis x squared plus 3x minus 5 plus quantity 2x plus 3 which then we could simplify this further. E to the 4x squared plus 12x minus 20 plus 2x plus 3, and finally wind up with e to the 4x times 4x squared plus 14x minus 17. And now, as far as what's the correct answer, it really depends on the class and what they accept as a correct answer. This is fully simplified. Depending on what, again, your professor is requiring, that might be considered, good enough for an answer. It really just depends on the preference of the instructor. So let's move on here. Let's do one more example here, the product rule. So let's look at the derivative with respect to x of the natural log of x. Whoops. The natural log of x e to the minus 5x. And then again here, this here is my f at x, and this here is my g at x. So again, to do this derivative, we just go through and do each one. Now the rule for natural log of x was simply 1 over x, so I get 1 over x times e to the negative 5x, and then plus natural log of x times, and I'm going to put it inside parentheses here. Let's go ahead and do that for all of these here, because we said it's important to do. And then I'd have negative 5e to the negative 5x. And the reason it's good to put them in parentheses here is that there is a multiplication that's going on here. It's not subtraction, it's multiplication. So if we were to do a first kind of little simplification step here, we'd have e to the minus 5x over x minus the natural log of x, minus 5 natural log of x e to the negative 5x. And then to simplify this even further, we could write this as e to the negative 5x 1 over x minus 5 natural log of x. So the reason I want to do this is being very careful when you're doing this exponent rule, especially when it comes in the second term. This isn't then suddenly minus 5 e to the negative 5x. There's still a multiplication, which is why I say it's always good to put the parentheses down first. That reminds me that these things are multiplying, not adding and subtracting. All right, let's move on to the quotient rule. The quotient rule is just kind of more, it's plug and chug is what, for the lack of a better term for it. So if you have the derivative of two functions and you're dividing them, for instance, then this is the same thing, or this is equal to, I shouldn't say it's the same thing as, it's f prime at x times g at x minus f at x g prime at x over g at x quantity squared. So it's kind of an annoying formula in some ways. And I'm going to do one or two quick examples with that. So a quick example with that would be, for instance, let's look at the derivative with respect to x of e to the 4x over x squared. Well, here, let's make that 3x squared minus 5x plus 1. And so just going to plug and chug through with the formula here. So this would be 4e to the 4x, because that's derivative of the f at x, times the bottom, 3x squared minus 5x plus 1. And then it's minus the top, which is e to the 4x, times the derivative of the bottom. So the derivative of the bottom is 6x minus 5. And then this is all over the bottom, quantity squared. And so again, depending on how your instructor wants you to simplify these things, you can maybe leave it as is there, but from the top, I would go ahead and factor out an e to the 4x, and I would be left with 4 times 3x squared minus 5x plus 1 minus 6x minus 5 in parentheses. That divided by 3x squared minus 5x plus 1 quantity squared. And then you can also do more simplification, and you'd have e to the 4x times, this would be 12x squared minus 10x, or 20x, I'm sorry, plus 4. Being careful with your sign, it would be minus 6x plus 5. And this is all over 3x squared minus 5x plus 1 quantity squared. And then finally simplify the top, and you get e to the 4x 12x squared minus 26x plus 9 all over 3x squared minus 5x plus 1. And so, in my opinion, not the most exciting rule to use, but sometimes we have to use it. Now there are times where you can actually cheat. It's not really cheating. I say where it looks like you have to use the quotient rule. Now, always pay attention to the problem. The problem tells you to use the quotient rule. You better use the quotient rule. But let me look at an example here, where you have x squared plus 3x plus 1 divided by e to the 4x. So this problem is set up to do the quotient rule with it. But if the problem doesn't explicitly say that you have to use the quotient rule, you could rewrite this as the derivative of e to the negative 4x times x squared plus 3x plus 1, and change it into a product rule by using negative exponents. Now you got to be careful when you do that, but and also you have to be careful because the problem says explicitly to use the quotient rule. You better use the quotient rule. Okay, the last special rule here is the chain rule. And this is really for composite functions. So the rule itself looks a little weird when you first write it down. It's saying if you have a function that's f at g at x, then this is equal to f prime g at x times g prime at x. So the way the rule is set up, I mean, that's the way it's set up, but it just, I think just going through some examples makes it a little bit easier to understand here. So let's just dive into some examples. So I'm going to look at kind of a silly example here, but I think it shows the power of the chain rule here. And I'm going to do this x cubed minus 2x squared plus 5x plus 1 to the 10th power. Now technically, you could multiply that all out, but that seems like it's kind of a pain to do. And so the idea here is that this inside here is your like g at x here. So instead, just think of this as like x to the 10th power. If you think of it as x to the 10th power, well then we know the derivative of that would simply be 10, and then I'm leaving big set of parentheses on purpose. It'd just be 10x to the 9th power. If it was x to the 10th power, it'd be 10x to the 9th power. We're going to do the same thing here, except we get 10, but then what we get, we don't just get x, we get the entire expression here. So 10x cubed minus 2x squared plus 5x plus 1 to the 9th power. But then the thing you have to do is you have to multiply by the derivative of what is, quote, inside the parentheses. And so what you have to do is you have to multiply by the derivative of what's inside there. So 3x squared minus 4x plus 5. And again, depending on how you're asked to write your answer, you might have to write this as like 30x squared minus 40x plus 50, because I multiplied in the 10 there on the second term. Because you can't multiply the 10 in on this first term, because you would have to first raise it to the 9th power and expand it, which I don't want to have to do that. So some people will accept this as an answer. Some people would want you to write that. Now this also has benefit of just even some very basic ones here. So for instance, a function that looks pretty simple here, derivative of, well actually let's just do the square root here. The square root of x. Well, let's not do the square root of x. Let's do the square root of 3x. So I mean, this looks like it shouldn't be hard to do. And it's really not, but this would be using fractional exponents. This would be 3x to the 1/2 power. Now if I take the derivative of this, I'm just going to use, technically I'm using my chain rule here, so it'd be 1/2 times 3x, subtract 1, so it's now negative 1/2 power, times the derivative of what was inside, so times the derivative of 3x. And of course the derivative of 3x is just 3, so you'd get 3/2 3x to the negative 1/2. And then again, depending on how your instructor wants you to write an answer, you might want to convert that back to rational form, which would be 3/2 times the square root of 3x. Now, for me, I just leave it as this term here. But again, that really depends on the instructor that you have. And so let's look at another example here. If you look at the derivative of the natural log of, well actually let's be No, let's not do that. That's a stupid one to do. Natural log of the square root. Let's do the cube root of x. And so this one here would be equal to, well, first, before I do any derivatives, anytime I see a radical, I'm going to convert it. And so I'm going to convert this to the natural log of x to the 1/3 power. So natural log is 1 over x. So we get 1 over x to the 1/3 power times the derivative of what's inside. So what's inside is x to the 1/3, which is, sorry, I just keep getting ahead of myself here, trying to make this quickly, and I jump ahead. We get 1 over x to the 1/3, and then this would be times 1/3 x to the minus 2/3. Now, you actually do want to simplify this, because simplifying this becomes a little bit interesting. So I'm going to first simplify this by doing 1 over x to the 3rd times 1/3 times 1 over x to the 2/3. But then we have x to the 1/3 times x to the 2/3. And you actually get to add those exponents together, so you get 1 over 3x, which is kind of interesting. One real quick last example here is, let's look at the derivative with respect to x of the square root of x squared plus 5x. Now again, anytime you see a radical, first thing to do is to rewrite this in fractional exponent form. And then we apply my chain rule. So I'm going to get that this is equal to 1/2 x squared plus 5x to the minus 1/2 times derivative of what's inside and then that's going to get me 1/2 x squared plus 5x to the negative 1/2 times 2x plus 5. All right, so hopefully that's been helpful.